All right, in this series, we're going to discuss asynchronous JavaScript. What exactly that means, what's the difference between asynchronous and synchronous code. We're going to talk about the event loop, how that works in JavaScript, and we're going to talk about the sort of the state of asynchrony in JavaScript, what kind of advancements have been made in the last few years with respect to asynchrony. Okay, so it can be kind of a complex topic, and I'm going to try to simplify things the best we can. To start with, however, we do need to have a quick segue into performance testing. So this is really simplified, really dumbed down way to performance test. We're basically starting a stopwatch and then running some code and then stopping the stopwatch. That's the idea, and we can do that with code. It's not at all perfect, but it does give you an idea of how fast an algorithm or a piece of code will execute. All right, and we'll examine some of the downsides of this, but it's nice to just give you a general idea. There can be lots of problems, of course, if you're running other applications in the background. For example, I'm recording this video, so that might have an effect on the overall performance compared to me running it without running the test without recording a video or something like that. So the load on a particular machine, the processor load, is always going to impact this, and we're actually going to see that. I'm going to run a demo where you're going to see how the performance time changes even within the same program. So it's not perfect, but it does give you a concept. It gives you an idea of how fast something runs. All right, so to start with, we're just going to log out two different ways of sort of starting that stopwatch and ending the stopwatch, right? The idea is we start a stopwatch, we run some code, and then we end the stopwatch, and that tells us how much time has passed. Okay, so the date.now object has been around for forever in JavaScript. It basically gives you the number of milliseconds since midnight the morning of January 1st, 1970. All right, there's historical reasons for that we won't go into now, but it's fairly standard. Now this is an integer. Okay, what's more recently been added is the performance.now function, and this gives you milliseconds, and it's a floating point decimal, so this is high resolution, and it gives you milliseconds the program has been running. And the context of what this means exactly is slightly different depending on if you're in the browser environment or the node environment, but for what we're doing, we're just using it as a start and stopwatch type of thing, so that's not particularly important. But what is important is this gives you a higher resolution value of the amount of time that has passed. All right, so let's take a look at the results from both of these. Let's get our terminal open. There we go. And we can run performance testing. I'm using JavaScript modules, so I'm trying to get in the habit of using .mjs. I also have this hashbang on the top of my file. In Linux and macOS environments, Node allows you to use this syntax to execute a script with Node, and that keeps me from having to type Node in front of each one of my file names. So that's just a small thing. So here, this is the number of milliseconds since January 1st, 1970. We can test that real quick. Update.now, and we should be able to divide that by this is milliseconds, so let's divide by 1,000 to get seconds. Let's divide by 60 to get minutes. Let's divide by 60 to get hours. Let's divide by 24 to get days. And let's divide by 365 to get years. Okay, and so this 2023 late in the year, so 53 years since 1970 and then some change. All right, so that's just proof that this works as I'm saying. But notice the difference. We have milliseconds here. It's kind of hard to read. You don't really know. We're only really interested in this part of it. But here with the performance.now, we actually see it took 48 milliseconds to reach this part of the code where we actually call performance.now, and then it goes and gets the system time, right? So that's what we're looking at, and we're going to try to do some really basic performance testing. This is not at all robust enough to use in a professional environment, but we're going to just use it as an example and run some tests. And this is really useful for you to be able to kind of explore things, right? So obviously you could set up all sorts of benchmarking for different pieces of code and real thorough testing, but if you just want to get a sense of something, this is a really handy way to do it. Okay, so it's very simple, non-robust. And we're going to test a simple piece of code. This is the 3x plus 1 problem you basically iterate over a certain number of loops, and you start with some value. And then if x is, we'll start this at loops. All right, and then x equals, so if we do like 1,000,000 here, x starts at 1,000,000, and then if it's odd, we multiply by 3 and add 1, right? And then if it's even, we divide it by 2. Okay, so to start out, if we did 1,000,000, that would be even, right? So we would divide by 2 and get 500,000. Next iteration, that's also even, so we would divide by 2 and get 250,000, etc. Right? So this process repeats and eventually seems to end up in some sort of cycle where eventually you get to some number that's already been reached before, and then the cycle starts. Right? It'll just continually repeat because this is a deterministic algorithm. Why did I choose this? It's just because it's a really simple piece of code. Right? That's it. So we're gonna have to run this several times to get a sense of how long it takes, and this is common for testing very fast pieces of code like this. Right? This should not take very long to run, so we have to run this like 10 million times or something to get a reasonable result. Okay, so here to start out with, I'm going to use date.now, and we want to get the initial time. So I've got the I'm also going to do this with performance.now. So this is date start. So we're using date.now here. Then we execute the code. Now it's really important that you don't do anything in between getting this. This is like starting the stopwatch and this is ending the stopwatch. Okay, don't do anything in between there. The only thing that you should do in between there is run your tests. Okay, now we are doing one tiny little thing, which is an extra function call, and then we're running our tests, right? But that shouldn't take up too much time, and we're running our tests so many times it shouldn't play any significant role at all. Okay, so but we start, run the test, and then end. Don't put console logs, don't put anything else in between the start and end, just your test. Then once we have that, we can take the time delta, we can subtract delta start from delta end, or date start from date end. Okay, and this should give us the number of milliseconds. Right, we can run this really quickly. All right, so time to complete, this took 23 milliseconds. And we can run it, and you can see there's some variance as I run this. And again, it's not perfect, right? There's some things going on in the background. It's hard to tell exactly what all is influencing. There's some context in the hardware, processors. I've got my processors up here. When I run this, there'll be a processor spike, and if I ran it long enough, potentially the hardware would decide to move that thread over to a different processor, and there's some context switching and all sorts of things going on the hardware level that can affect these times, but it still is reasonably consistent in terms of milliseconds. That's good enough for me. I can't tell much of a difference between those things. However, algorithms can, and that amount of time can be very important depending on what you're doing. All right, so let's do the same thing with the higher resolution now function. So this is performance.now. Okay, we got the same thing. We have p-start. We need let p-start and let p-end. Okay, so here, let's just make sure we have the same 1 to 3, 1 to 3, 10. Okay, 10 million, and then 1 to 3, 1 to 3, 10 million. Okay, that looks right. And so this is exactly the same thing. The only difference is we're using performance.now. All right, so we can run this. Okay, and so the first one, 22 milliseconds, and this, you see this higher resolution, much higher resolution. We get a lot of detail about how long this took. All right, now the first one, this is kind of odd. It has something to do with initially starting up the process. This first one is always more, and this is significantly more. Now it could be other things are going on in the background. It could be residuals from just firing up node altogether. So I'm not exactly sure why the discrepancy is here, but it's important to know that that sort of thing can happen in your performance tests, and I can show you if we move the performance now part up to the top, right? We will see that this one will be longer instead of this one. And we'll go ahead and still run this one too. Let's copy and paste this a few times. All right. So we run this. Okay, and so now we see that this one is longer than the 22, then the 22, then it gets faster. So as I said, there are lots of things that can be impacting this, but initially there is something that makes these first ones start off a little bit slower, right? And we could even put this in a loop and then see, you know, for do this like 100 times, right? And we could kind of just view that. It's a fast enough. So, right, we're 100 times 10 million, right? This is like a billion executions. So this piece of code is really fast, right? And it should be. It's just basic math, right? We can get rid of these. All right, and we'll do 100 of these, and we'll see what kind of variance we get. Let I equal 0. Okay, so variance throughout, right? And some of them are a lot longer, but it's generally speaking around 20. And you look at the beginning, it's a little bit slower, but that's not the slowest one too. So there's lots of reasons this can change, right? But it does give you a good idea. All right, so that's sort of the side thing I want to talk about performance testing, because what we're going to do is analyze asynchronous versus synchronous code, and we need to know how long certain things take to execute, right? All right, so let's pop over to this window, okay? What we want to do here, we're going to talk about what it means to be asynchronous. In JavaScript, they say JavaScript is single-threaded. You've probably heard that lots of times. What does that mean? It means JavaScript, by its nature, is synchronous. One thing is executed at a time. When that one thing gets done, the next thing starts executing. Okay, so you have a call stack, a stack of things as you execute a function, and any functions inside of that things get added to the call stack. And I'll have a diagram for this here in a little bit, but the idea is things run synchronous. We start the file, we get to the first line of code, that executes. Once that's completed, we go to the next line of code. And even within a line of code, there is an order of things. For example, I can't call this function.log until I evaluate what I'm going to pass in as an argument. I can't pass this thing in as an argument until it's evaluated, because this is a format string or a template string, and I can inject JavaScript expressions inside of it. So I have to evaluate this expression first, then this gets injected into the string, then I have a string, so then I can call console.log. So there's an order of execution, all right? But it's synchronous. Now the easiest way to achieve mimicking asynchrony in JavaScript is with the set timeout function. So the way the set timeout function works is you set a timeout. The first argument of this function is a anonymous function, or any function, but this is, you'll see this commonly where someone just defines an anonymous function as that first argument. Functions in JavaScript can get passed as arguments all the time. They are considered first-class citizens. That's what that means. So this function is what's supposed to be executed after this time frame. This time frame is in milliseconds. Okay, so basically what happens when we call set timeout, there's some sort of registry that JavaScript is keeping track of these timeouts and periodically checking to see, has this timeout expired, right? Has this amount of time passed since we called set timeout? Now it's important to note that this guarantees only that 1,000 milliseconds have passed since you called set timeout. It does not guarantee that this function will execute in 1,000 seconds. It just means it will not execute before this time. So if JavaScript is busy, it's single-threaded, so it could be doing something else. This might not get executed for 6 seconds, and I'll show you an example of that here in a minute. All right, so let's first see how this works. So we're getting start performance.now. So start minus start should give us 0, right? And then the ending time is performance.now minus start. Okay, and then in our set timeout, we have this as async A, and we're going to have a few different asynchronous calls. And so we're doing a performance.now minus our initial start value up here. Okay, so we should see how this flows in synchronous code. Okay, performance. There we go. Copy and paste got me again. All right, there we go. Run that. Okay, so start is 0, end plus 4. Okay, so that's 4 milliseconds. But async A was 1,005 milliseconds. Now, initially you might think, well, that doesn't make any sense because this function was defined up here, right? But this is just a function definition. It's not when the actual function is called. This, again, remember, maps this function to a registry that JavaScript keeps track of, and it checks periodically if this time has expired. Once it expires, that is when this anonymous function gets called. So it makes sense that this anonymous function would be more than 1,000 milliseconds, right? Since the start of the program, right? And we saw even here, this is occurring after we are registering this asynchronous timeout. Okay, so this is after all of this registration happens. So some time has expired and approximately 4 milliseconds has taken place from the time we called start to registering this. But registering this is not the same thing as calling the function we are testing. Okay, so let's take a look at a couple of more of these functions, right? I guess copy and paste over here. Trying to save you the pain of watching me type all this stuff out. Okay, so we have async B and async C. And we're going to take some time. Let's say this is 3,000, this is 2,000, and this is 1,000. So we're actually registering this timeout first, right? Async A, and it should come in at 3 seconds later, though. And this is going to be 2 seconds later, and then 1 second later. Okay, now it's pretty close to 1,000, right? So this gives you sort of the sense that, you know, as I said, it might make you think that this will occur in exactly 1,000 milliseconds. That's not the case. It just will not occur before 1,000 milliseconds. And I'll give you an example. We can do this real quick. So after we've registered the set timeout, normally what we did in the code before is we just went ahead and logged in this ending time. But what we're going to do now is add some synchronous code that takes a long time. Okay, so we can just add a for loop. Well, we can probably just grab one of our performance tests if we wanted to, right? Grab this performance test, and then, you know, call test me. We've got milliseconds, so let's go. We need to probably go in the billions here. 1, 2, 3, 1, 2, 3, 1, 2, 3, maybe 10 billion. All right. And then we can run this. Some time passes, hopefully more than 3 seconds. I should have started a little smaller. Let's do 1 billion. Okay, so it looks like I do need a little bit more than 1 billion. So end is at 2 seconds, right? 2.087 seconds, right? So that means this took approximately, including the registration, so we're registering these timeouts and then executing this, that took almost 3 seconds. Okay, now notice async C we have the timeout set for only 1 second, right? But how long did it take before it was actually executed? It took more than that 1 second, right? It took 2 seconds. And so did B. The reason is it can't check to see, JavaScript can't check to see if these timeouts have, if the time has been reached yet, since the time they were registered. It can't check that because it's actively doing things, right? That is synchronous JavaScript. When there is a thread of synchrony in JavaScript, it has to complete before we can check for further events or further asynchrony. Okay, that's an important concept. All right, and we're going to talk in detail about this in the next video. But anything that's running synchronously in JavaScript has to finish before we can check to see if anything else needs to be run. So that's the difference between synchrony and asynchrony. Asynchrony is basically a list of synchronous things that need to be done. Once one of those synchronous things executes to completion, then we can check to see if anything else needs to be run. If so, we take it off the event queue and start executing that synchronously. But we can't check to execute anything else until that one synchronous thing finishes executing. All right, so that is sort of the heart of the matter of asynchronous JavaScript, right? It's all synchronous. JavaScript is single-threaded and it's synchronous, but what you have is different compartments of synchronous code that they don't have to be run in any particular order. That's the asynchronous part. Okay, so you grab one synchronous bit of code, run it to completion, and then you can check to see if there's anything else that needs to run. And this is important when you think about the context of a browser, because when you first load up some JavaScript, the JavaScript will execute, and then there's nothing to do. It just sits there most of the time waiting for the user to interact. There's a concept of events on the browser. Every event can have a function associated with it, or a JavaScript execution context. All right, so that function, we can just think of it as function, executes when the event occurs. And so in the meantime, JavaScript is just waiting for some code that needs to be executed. It's waiting for something to be added to the event loop. When something's added to the event loop, or the event queue rather, it pulls it off, and then that's a blob of synchronous JavaScript. So it's going to run that synchronous JavaScript. And sometimes when running that synchronous JavaScript, we can register new blocks of synchronous JavaScript to be executed later, asynchronously. Okay, so this is basically registering a chunk of code to be executed at a later time. All of this inside of this function is going to be executed synchronously, but not until this expires, right? Okay, so that's the basic idea. And we can mimic this concept of a set timeout. We can have a set timeout synchronous, right? I could do something like this. Set timeout sync. And the idea here is just like set timeout, we're mimicking the interface of set timeout. We have a function callback essentially, and we're going to hear that term callback a lot, and then a delay in milliseconds. Okay, and so what I'm going to do I'm going to mimic set timeout, but in a synchronous fashion. Okay, so we're going to have time is performance.now plus the delay. Okay, so this is the time when we should execute this thing. All right, and so all we do if we want to mimic set timeout synchronously is we repeatedly call performance.now over and over and over and over again. And as soon as performance.now gets to be larger than the initial start time plus the delay, that means it's time to execute our callback function. Okay, and callbacks are really common. You'll see them a lot in terms of asynchronous JavaScript, right? As soon as you do something and you don't know how long that thing's going to take, when it gets done, it has this callback function, and you call back, and it finishes whatever it needs to finish via that function. All right, so how does that look? Let's change all of these to set timeout sync. All right, and we can do something like that. I had this everywhere. I switched from the date.now. I was just going to use date because everybody's familiar with that, but I decided to add in the performance stuff the last minute. Of course, I didn't test it. All right. Okay, so I can mimic the synchronous the timeout, right? I still have a timeout. It's still taking a lot of time, but the difference here between the synchronous version and the async version, if we go up here, async version, C took 1 second, B took 2 seconds, A took 3 seconds. Now the wait times are additive because we don't even register this one until this whole thing completes, because this set timeout synchronous is indeed synchronous, right? So with asynchronous code, right, this becomes synchronous now. With asynchronous code, we register all 3 of these right away, right? With synchronous code, this entire time has to expire before we can even register this delay. So it's 3 seconds plus 2 more seconds, right? Which is why the next one is 5. And then C, it takes 6 seconds, right? Because it has to go through these. And in asynchronous, C was the fastest. It executed after 1 second. And also take a look at my processor cores up here. All right, so we see the node is single threaded. You might see it jump to another processor. You know, so here it switched over to another processor and then exited, right? So you'll see the hardware, you know, switching that thread execution from, you know, different parts of the processor based on heat or performance or various different things, right? But we see that took about 8 seconds total, right? And C, instead of taking the 1 second, like it did up here, that was the fastest one, it ended up being the slowest one. Okay, and just for context in this file, we can do all of them. We can have the asynchronous ones back, and then we'll have the synchronous ones. All right, so actually I guess this should be sync A, sync B, and sync C. Okay, so what do we think is going to happen here? We have the asynchronous set timeout. It's going to register asynchronously, 3 seconds, 2 seconds, 1 second. Then we have the synchronous executions, right? And then we're running some code afterwards, right? So how long is it going to be before, you know, we can comment this part out for now. We don't need this part because we have this synchrony. All right, how long before, let's say, async C executes, right? So we're registering it for 1 millisecond. So take a second and try to think what is going to happen. What's going to happen is this all happens really quickly. We're registering the set timeout. Basically, that they're sort of a type of event. That registration takes almost no time. Then we synchronously wait, right? So we have to wait 3 seconds. Then this will print. Then we synchronously wait 2 more seconds. So that's going to be 5 seconds. And then this one will run. Then we'll synchronously wait another second. And this one will run. And so that'll be 6 seconds. And then the synchrony will have stopped. We'll execute this end. The synchrony will have stopped because all of this is synchronous so far. And we finally got to the end of our JavaScript context and the synchrony is over. So now JavaScript can switch and check to see if there's any asynchronous chunks of JavaScript that need to be executed. Okay, and then all 3 of these, their time will have expired. So these will all run back to back to back. All right, that's the idea. So let's run this. Okay, 3 seconds for A, another 2 seconds for B, and then another second for C. So 6 total. Then we get to the end of our file, right? This is the end of our synchronous execution of JavaScript, right? And then we have async C, B, and A all running. And the order of that is hard to determine. It's probably the order of the registration. Let's see. A, B, and C. Is that the order that we got? No, it actually isn't. So it's not clear how JavaScript tracks these timeouts. especially when they're all ready to be executed right now. So the promise was, I will not execute this before 3 seconds. I will not execute this before 2. I will not execute this before 1. Right? So that's the contract, and it did respect the contract. Right? None of those were executed before the times that was stated. All right, and just for, we'll talk about this in the next video, but just for sort of a visual representation of what's going on here, you have the idea of an event loop, and we have some JavaScript executing, right? This always has to complete. Whatever JavaScript chunk we're executing has to complete before we grab something else from the event queue. When we added the set timeouts, it was adding timeouts to this event queue. Once this finishes executing, we can grab the next element, the next chunk of JavaScript, and start executing it. Okay, and then grab the next one and start executing it. Once we've executed all the JavaScript, there's nothing in the event queue, and then the website just sits there. It's waiting for you to click a button or something, and then once you click the button, that's an event. The event has some JavaScript associated with it. We pull that JavaScript over it and start executing that synchronously. Okay, so we'll look at this in more detail in the next video.